right, so we're continuing in learning more about electric circuits. And so before I start drawing some more circuit diagrams and analyzing circuits, I want to review some of these concepts that we've talked about and maybe you've heard about and kind of relate them to each other. So the first concept that you guys are familiar with is force. You've learned a lot of forces. In here, we're talking about the electric force. And so we have a law for the electric force. Looks like this. What law is this? Coulomb's law, right? So it says the force is proportional to the charges and inverse squared proportional to the distance between them. So if the two charges get further apart, the force gets weaker. If they get closer, they get stronger. And the bigger the charges, the stronger the force. And also law of Paul Abdul's in there because of the minus signs. Any questions about Coulomb's law? All right, the next concept that you guys have probably heard of is the electric field. And the electric field for a point charge looks very similar to the Coulomb force. What's the difference? Yeah, it's missing one of the charges. So it's also inverse squared proportional. If it gets further apart, the electric field gets weaker. And it's also proportional to charge, but it's missing the other charge. So we call the force law an interaction because it involves two charges. So you have to have two things, and they interact, and they feel a force between each other. It's the same thing with Newton's law of gravity, too. You have the Earth and the Moon. They're two objects. They feel a force. The electric field is a field. It's not an interaction. Now, you can make it an interaction by multiplying it by the charge. And so there's a connection between the electric field and the force, and that connection is that F is equal to Q times the electric field. I'm going to put Q1 here just to label it. So if you take the electric field here and you multiply it by Q1, you get back to the force law. So really, they're very similar concepts. Just one is a little bit simpler because you only have to worry about one charge. And so you can do your calculations with forces, or you can do your calculations with electric fields. You should get the same answers, but sometimes working with one or the other is a little simpler. What do these guys have in common? Anything? Well, the K constant, yeah. They also have the inverse squared proportionality. They also have charges in them, but what I'm looking for is their vectors. So vectors have components, it's magnitude and direction. All right, the other concept that you guys are familiar with is work and energy. What's the units for work and energy? You guys remember? Joules, good. So the potential energy between two objects is minus K Q1 Q2 over R. So this is kind of similar to force. What's the main difference between force and potential energy? Good, it's not inverse squared, it's 1 over R for the energy. The other main difference is that it is a scalar. It's not a vector. Now remember you guys learned how to, you had a block on a hill or whatever, and it would slide down. You guys had to identify all the forces and do all this summing up the forces, setting them equal to MA. And then later you guys would learn work energy, and you can do all those same type of calculations again with the ideas of work and energy, and they were a little bit simpler. Why were they simpler? I always felt tricked when I first learned how to do that because they taught me the hard way first, and then they taught me the easy way. They're simpler because they're scalars. You don't have to worry about the components. So forces, you had to worry about the x component, the y component. With work energy, you just have to worry about how high it is and where it ends up, right? Any questions so far? All right, so the connection between these guys is that U is equal to negative, F over R. And for those who know calculus, it's also U is equal to the negative gradient. No, F is equal to the negative gradient of U. So it's the other way around. Sorry. minus U over R. Yeah. So U, we take U and we put minus R, we get back to F, right? All right. So these guys are connected now. So that means any calculation you can do with forces, you could also do with energy. So you can choose which one you want to do, whichever one's more convenient. And then the last one I want to talk about is electric potential, which is also called the voltage. All right. It's a little bit funny to me to call it the voltage because, you know, the force, the units are newtons, but you never ask somebody, what's the newtons? But you ask somebody, when you're asking for the potential, you ask them, what's the voltage? Seems a little weird to me. So the potential is similar to both the electric field and the potential energy. How is it similar to the potential energy? Good, you're telling me the connection, right? So he said it's the energy per point charge. So if you take V and you multiply it by Q, you get the potential energy, right? So it's the same type of connection here. But what I like about them is they're both scalars, so I don't have to worry about components. And the next nice thing about the electric potential is it only depends on one Q. So in a way, it's taken away as much as you can from the problem and simplified it. It made it a scalar, and it made it depend only on one Q. And so, for instance, if you were interested in how charges interact with each other, and you have a wire of charge, so you have in a wire there's like Avogadro's number of electrons. All right, do you want to calculate the forces, the interactions between all Avogadro's number of electrons? I don't want to do it. I don't even think it's possible to do it. I don't even think a computer can do it. But if you work with the potential, you don't have to worry about all the electrons. Okay? You just have to know the potential of the battery, use Ohm's law. If you know the resistance, you can find the current. All right, what's the connection between this guy and this guy, the electric field and the electric potential? Anybody see it? Similar to this guy. E is equal to V over R with the minus sign. I don't like this chalk. Can you guys see this? So if you take this guy and you multiply it by negative R, you get the electric field. So these concepts are all connected. That's what I'm trying to show you guys. And so you'll hear people talk about one or the other solving a problem. They're just picking the one that's most convenient for the problem that they're solving. Kirchhoff's laws. All right, so let's draw a circuit real quick. Draw it down here. All right, so we have a battery here. The voltage, we have a resistor. Every circuit should have some resistance in it, a resistor. And the voltage drives the current. What's the relationship if I gave you what the voltage was and what the resistance was, could you tell me what the current is in the circuit? So let's say the voltage is 2 volts, and I give you a resistor of 10 ohms. What would be the current? V equals IR, right? So if V equals IR, then I should be equal to V over R, which is 2 volts over 10 ohms. Which is 1/5 of an amp, yeah? Good. All right, so now we're going to learn two laws that are also almost as simple as Ohm's law. They're called Kirchhoff's laws. And the first one is that the sum of the voltages around a closed loop is 0. All right, so if we're looking at this guy, and this is a loop, right? It's a closed loop. So I can apply Kirchhoff's first law to it. If I start over here, I usually like to start before the battery. And I start analyzing this guy, and I say, oh, here's the battery. That's a voltage, right? I guess 2 volts. And then I get all the way over here to the resistor, and I say, oh, there's a voltage between the resistor here. We know that because last week we measured voltages between resistors, so we saw that there's a voltage. What did you measure last week? Do you guys remember for that voltage? If this was 2 volts, what did you measure over here? 2 volts, right? So I'm going to put minus 2 volts because, actually, call it B. So this was 2 volts minus 2 volts, which happens to be equal to 0. So the sum of the voltages around this loop was 0. All right, as long as you call this negative. So we're always going to call voltages across resistors or any element other than a battery negative voltage. And that way, when we sum up the 2 voltages, so this is the voltage of the resistor, we get 0. So you guys already showed Kirchhoff's first law is true last week. You guys just didn't know it was Kirchhoff's law. Any questions? All right. There's a mathematical way of writing this too. It says that the sum of the, I mean, I can't say it any differently. The sum of the voltages is equal to 0. So this is a sigma. It means add them up. You take all the voltages in the loop. They should equal 0. I'm going to write loop here just to remind people that that's a loop. So this is an index I. It's just saying count over all of them.
Good question.
Yeah.
So you said that most circuits, or all circuits, require a resistor. Is that what you said?
Yeah.
Is that just so it doesn't affect the battery?
Well, let's think about it. What if you didn't put a resistor in a circuit? What would happen to the current? Yeah, it would blow up. It would get huge. And so eventually your circuit would melt. So that wouldn't be a good idea. So it's probably a good idea to always put a resistor in your circuit just so your circuit won't melt. Also, the wire always has some resistance in it, right? So even if you don't put a resistor in there, there's always some resistance. Good question. Are you ready for the second Kirchhoff's law? All right, I'm going to draw a little picture here. So this was a very simple circuit. I'm going to draw another circuit that has something a little bit different about it. What kind of circuit is this?
Parallel.
Yeah, we had resistors in parallel, which we learned last week. All right, and so Kirchhoff's second law says that the sum of the currents at any node is 0. All right, so let's look at this circuit here. It's got a battery. It's going to drive a current. By the way, this is called a node here. This is also a node. What happens to the current when it hits the node? It splits up, yeah. So there's going to be some of the current going this way and some of the current going this way. All right. And let's say you measured this guy to be, let's say these are equal. I already made them equal. Equal resistances, just to make it simple. And this current here was 2 amps. What should I1 be then? If the total current coming into the node is 2 amps, and these are equal resistors, the current is going to split. And since they're equal resistance, they're going to split equally. And so we're going to have 1 amp over here and 1 amp over there. Okay, so if we had 2 amps coming in, 1 amp going out this way, and 1 amp going out the other way, what do we get? 0. And that's what Kirchhoff said. It's just conservation of charge, right? Like, I mean, charges aren't appearing and disappearing, so if it came in, it has to go out. All right. Are these pretty simple laws? Could you have come up with these laws? I always think I could have. If I was only like born 200 years earlier, these would have my name on them. All right, any questions so far? All right, so I'm going to write this in a mathematical form, which says that the sum of the i's has to be equal to 0. And I'm going to write here to remind you guys, node, any node. All right, let's apply these to a couple circuits here. R1, R2, R3. All right, so now I did the same thing here, but I just added more resistors. And so let's apply one of Kirchhoff's laws. Which one should we apply here? Can we apply the second law? No, there's no nodes. So the only one we can use is this one. So let's use it. So what do? I add them up, right? Well, let's start over here at the battery. So the first thing I'm going to hit is the battery. It's V, maybe 2 volts, whatever it is, it's V. And then I'm going to get to the first resistor. What is the voltage drop across the first resistor? Well, it's something, right? But we can use Ohm's law and say that it's minus IR1. Well, it's also the current going through this guy is I. I could put I1 here, R1, but we already know that the current going through these is all the same, right? Because last week we proved that. We measured the current going through each one, and we saw it doesn't matter. There's no nodes. It can't split up. And then we go to the second one. We do the same thing, I, R2. And then the third one, I, R3. And I'm running out of board space, equals 0. All right, great. We applied Kirchhoff's first law, and we received half the points on an exam. All right, what should we do now? Any ideas? There's a common factor here. Yeah, so I'm going to move the V over to the other side, and I'm going to factor out the I. So there's 2 steps there. So what will I get? I'll get V is equal to I R1 plus R2 plus R3. All right, so 2 steps of algebra, and you get to here. And this looks like V equals IR, right? Except the R is the sum of these things. So I'm going to write V equals IR equivalent, where R equivalent is equal to what? The sum of the resistors. This looks familiar though. We already knew that, right? So for resistors in series, the equivalent resistance of the circuit now is the sum of the resistors. So Kirchhoff's law tells us something we already knew. All right, let's apply it to parallel. I'm going to do 3 resistors in parallel. R1, R2, R3. There is a node here. Let's apply it at this node. So what does Kirchhoff's second law say? The sum of the currents at any node must sum up to 0. So we have some current going in, I. We have a current going through each node, I1, I2, and I3. So it says I minus I1 minus I2 minus I3 must be equal to 0. But what is I1? It's V over R1, right? I'm going to write I minus S. This is 2. Then we got V minus V over R2 minus V over R3. Does everybody follow? Any questions what I'm doing here? I'm just applying Ohm's law to these I's. Why are all the V's the same? Why didn't I write V1 and V2 and V3? Because it's in parallel, and last week you guys measured each one of these and you decided that it wasn't the sum that equals it, they all get the voltage of the battery. So each one of these all has the voltage of the battery, therefore I only have to write the voltage of the battery here, not V1, V2. All right, so this is the step if people are taking exams that they get confused about. They usually remember to apply Ohm's law, but they forget that these are all the same V. All right, so I'm going to do a couple steps of algebra. I'm going to move the I to the other side and factor out this common factor of V. And I get V R1 plus R2 plus R3 equals I. Is that right? 10 times harder doing algebra on a chalkboard in front of people. And so then V is equal to I, and this chalk is dying, times something, right? And that something is 1 over the 1 overs. And I'm not doing this very clearly because I ran out of board, but we can see that the R equivalent here is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Well, we already knew that, right? All right, so if we already knew these results, why am I teaching you guys Kirchhoff's laws? Does anybody know why? Because I like to torture you guys? No, it's not because I like to torture you guys. It's because today we are going to analyze a circuit that you cannot use these simple rules here. So if you have simple circuits or trivial circuits, sometimes they're called, you can apply these two parallel and series rules in some combination and figure out the equivalent resistance of the circuit. But some circuits are not trivial or not simple circuits. And today we're going to analyze one. It's called the bridge circuit. And it looks like something like this. All right, so it's sort of diamond shaped, and it has a resistor across this part. Now, if I had a resistor across this part, it would be just parallels, right? A couple of series and parallels, and you can use a combination. And the fact that it goes this way makes it a non-trivial circuit. And that means we can't use these two laws, and the only way to analyze them is with Kirchhoff's laws. Well, the way we're going to analyze them is with Kirchhoff's laws. All right, so how do you analyze it? Well, you can pick some loops. How many loops are here? There's a loop here you can apply to. There's a loop here you can apply it to. There's also a loop here. There's lots of loops is my point, right? You're going to pick 3. I don't want you to do all of them. I don't even know how many there are. There's a lot. Sum them up the voltages and make sure they equal 0. There's a node here, there's a node here, there's a node here, and there's a node here. Pick 3. Sum up the currents. Make sure they add up to 0. All right. Any questions? All right, you guys can get started.